In the last lecture, we saw in detail what is convolution operation and how to perform the convolution operation, and now I will explain the properties of convolution operation. It is an important topic. It is important because you can obtain your answer in very less time using the properties of convolution. For example, in the examinations which are based on multiple choice questions, you can obtain the correct option very quickly using the properties of convolution. So it's good to remember all the properties of convolution. We will discuss 10 different properties of convolution operation, and in this particular lecture we are going to discuss 4 properties out of 10. So this lecture is part 1 of properties of convolution, and let's start our discussion with the first property. The first property is known as commutative property. Commutative property. Let's understand what do we mean by the commutative property. Let's say I have two signals. The first signal is x1t and the second signal is x2t, and I want to convolute them. So x1t convolution x2t, and let's say the final signal or the resultant signal after the convolution is yt. So what we are doing here, we are fixing x1t, we will convert it to x1 tau, we will replace t by a dummy variable tau, we will have x1t, we will fix it, and from x2t we will obtain x2t minus tau, and we will move it, and then we are getting the total amount of overlap using the convolution process. So yt is the signal after performing the convolution. Now according to commutative property, we will get the same signal if we convolute x2t and x1t. This means here we are obtaining x2 tau and then we are fixing it, and x1 tau is converted to x1t minus tau. We already know the process to obtain x2 tau and x1t minus tau. If you don't know, you may watch the previous lecture, and this time we will move x1t minus tau. So you can see the difference between this convolution and this convolution. Here we have x1t convoluted with x2t. Here we have x2t convoluted with x1t. So the position or the movement of the signal during the convolution does not matter. You will get the same signal. But it is important for us to understand the commutative property from the system's point of view. So let's take one system, and the impulse response of the system is given. Let's say the impulse response is ht, and we already know impulse response is used to define the linear time invariant systems. So we have one LTI system whose impulse response is ht, and the input to this system is xt. So we have impulse response, we have input, and we are interested in calculating the output yt of the system. And we already know the output yt of the system can be calculated if we convolve xt and ht. Now according to the commutative property, xt convolution ht will be same as ht convolution xt. So here the role of input and impulse response is switched. In this, ht is the input and here xt is the impulse response. But in this case, xt is the input and ht is the impulse response. So we can have a system whose impulse response is equal to xt. The signal xt was acting as input in this case, but in this case it will act as the impulse response, and the input will be the impulse response of this system. We will have the same output yt. This output yt is same as this output yt. So this is from the system's point of view, and I hope you now understand what is the commutative property. Now we will move to the second property, The second property is known as the associative property. To understand this property, let's say we have three signals, x1t, x2t and x3t, and we are convolving signal x1t and x2t first. So we will have x1t convolution with x2t, and the output of this convolution is convoluted with signal x3t. And let's say the final signal is equal to yt. Now according to associative property, if we convolute signal x2t and x3t first and then convolute the result of this convolution with x1t, we will get the same signal. This means we have three signals, x1t, x2t and x3t. Now instead of convoluting x1t and x2t first, we will convolute x2t and x3t first, and the result of this convolution is convoluted with x1t. So this is the associative property, and now we will understand this from the system's point of view. And for this we will take two different systems, and the input to the first system is equal to xt. The input to the first system is equal to xt, and the impulse response of the first system is equal to h1t. h1t with input equal to xt. Let's say the output is yt. So yt is equal to xt convolution h1t, and now we will convolute the convolution of these two signals with another signal, which is the impulse response of the second signal connected in series with the first signal. h2t is the impulse response. So the final output, let's say y dash t, is equal to xt convolution h1t, xt convolution h1t, that is yt, and then it is convoluted with h2t. Now according to associative property, if we convolute h1t and h2t first and then convolute it with xt, then also we will get y dash t. So this time we have one system only, and the system is having the impulse response equal to h1t convolution h2t, and the input to the system is xt. The output of the system is y dash t, and it is equal to xt convolution with h1t convolution h2t, h1t convolution h2t. So this is how the associative property is related to these systems. Here we have two systems connected in cascade. The h1t is the signal which is acting as the impulse response of the first system. h2t is the signal which is acting as the impulse response of the second system, and we want to represent the two systems as an equivalent system. This is first system, this is second system, and this one here is the equivalent system. So the equivalent system will have the impulse response equal to h1t convolution h2t. So this is very important property. Whenever you have two or more systems connected in cascade, then the equivalent system will have the impulse response equal to convolution of all the impulse responses. So this is how the associative property is implemented from the system's point of view. Now we will move to the third property. The third property is the distributive property. Distributive property. To understand this property, I will take three signals, signal x1t, signal x2t and signal x3t. x2t and x3t are added together, and we have a new signal which is sum of x2t and x3t. Now we want to convolute signal x1t with the sum of x2t and x3t. Let's say the final signal is yt. Now according to distributive property, yt will be same as x1t convolution x2t plus x1t convolution x3t. So this is the distributive property. You can think of opening this bracket and this will give you this result. Now we will understand this from the system's point of view. I will take two different systems. Let's say this is our first system and the impulse response of this system is h1t. Now we will connect another system in parallel with the first system, and the impulse response of the second system is h2t, and we will apply one common input to the two systems. The impulse response of the second system is h2t. So signal xt is there, which is the input to the first system, and it is also the input to the second system. Now the output of the first system is, let's say, y1t, and it is equal to xt convolution h1t, xt convolution h1t, and the output of the second system is, let's say, y2t, and it is equal to xt convolution with h2t. And now to get this result, we will add the two outputs y1t and y2t. We will add the two outputs, and the final output is, let's say, yt. It is equal to xt convolution h1t plus xt convolution h2t. Now according to the distributive property, this result can also be written as this result. So what we will do, we will add h1t and h2t, like we added x2t and x3t. We will add them. So we will have one equivalent system, the equivalent system of the two systems connected in parallel, and the impulse response of this system is h1t plus h2t, and to this system we will apply the input xt, which is the same input. We will have the output which is same as this output. It is equal to xt convolution inside the bracket h1t plus h2t. So from distributive property we have one important result. Whenever two or more systems are connected in parallel, then you can have one equivalent system having the impulse response equal to the summation of respective impulse responses. So the two properties, distributive and associative, are very important. From here we have the equivalent system of the two or more systems connected in cascade manner, and here we have the equivalent system when two or more systems are connected in parallel. Now we already know the LTI systems are defined using the impulse response. So the equivalent system is having the impulse response equal to the convolution of respective impulse responses. And in this case, the LTI system, which is the equivalent system, is having the impulse response equal to summation of respective impulse responses. So this is all for the third property. Now we will move to our fourth property. The fourth property is an important property, and you can call this property of delta function. It is property of delta function. We already know the delta function is nothing but the impulse signal or function. So this property is related to the impulse signal. I will write down the property quickly. If you have signal xt and you are convoluting it with delta t minus t1, then you will have xt minus t1. To remember this property, simply replace this t by t minus t1. Whatever you have inside the bracket of the delta function, put this t minus t1 in place of t in the signal xt. So this is one important property. And when t1 is equal to 0 in this property, let's see what we have. When t1 is equal to 0, we will have xt convolution with delta t equal to xt. So remember all the different forms of this property. This is the first form you need to remember. xt convolution with delta t minus t1 is equal to xt minus t1. And the second form is like this. xt convolution with delta t is equal to xt itself. Now we will see the another form of this property. Here the weight or strength of the impulse is equal to 1. Here we have 1. So weight or strength of the signal is 1. It is unity impulse signal. But if weight is not equal to 1, but the weight is equal to some value, let's say a, then we will have xt convoluted with delta t minus t1. The weight will be a and it will be equal to a times xt minus t1. In the same way, when we have t1 equal to 0 in this property, we will have xt convoluted with a times delta t and it is equal to a xt. You can remember all the different forms. And now we will try to solve two examples based on this property. In the first example, signal xt is a ramp signal. In example 1, signal xt is a ramp signal, and we have rt convoluted with delta t minus 2. From this property we can write rt minus 2. So this is your answer. You can see how quickly you have obtained your answer by using the properties of convolution operation. Now let's see example number 2. In example number 2, we have ut plus 3 convoluted with delta t minus 1. We will use this property again. In place of t, we will write t minus 1. So this will give us u t minus 1 plus 3. Simplifying this, we will have u t plus 2. So this is the answer. So this is all for this presentation. We have seen 4 important properties of convolution operation. If you have any doubt, you may ask in the comment section. In the next presentation, we will discuss 5th and 6th properties of convolution operation.